Welcome to the 17th lecture on mechanics of machining. Today I am going to discuss about grinding of metals and mechanics of grinding process. Grinding is also a machining process, but it is usually employed for finishing. It can also be used to remove the large volume of difficult to cut material. Suppose some hard material is there, we can actually grind it. It may not be able to use single point cutting tool of HSS material or carbide material. So, we do like that. So, we are going to discuss about mechanics of grinding process. Before that, we will discuss about some concepts about grinding of metals. So, grinding is an abrasive machining process that uses a grinding wheel as a cutting tool. It is called abrasive machining process because material is removed by abrasion. They actually abrade the surface. These small cutting tools, there can be small cutting tools are there. Basically, they are abrasive grains. So, these cutting tools are the sharp edges of the abrasive grains. If you have abrasive grain, it may be having number of sharp edges. Suppose this is the grinding wheel, it is the bond material. In this, there are number of abrasives they have been put and they are having multiple cutting edges. No? This one, this is cutting edge, this is also. And what will happen that after at the surface, maybe some cutting edges are exposed, like here this edge is exposed, this edge is also there, but that is far away. So, these are called active grains. There are grains inside also, they are inactive grains. If these grains will be broken and they will be removed, then naturally the new grains will come and they will become active grain. So, initially there are some active grain, some passive grains are there. After sometimes those grains which are passive, they will become active and this process will go on. And chips are removed. Suppose you give the feed motion, let us say workpiece is moving in this direction, then you are giving the feed motion and material is removed by small chips, like this is one grain and you are removing that. So, this way process goes on. Abrasive grains are mixed with a bonding agent. Here there is a bonding agent. Basically, in this you get bonding agent. Okay, so bonding agent. So, bonding agent is there and it is pressed or cast into the required shape and baked in kilns or electric furnaces. Whole thing baking is done. Grinding wheel manufacturing process we will not discuss in detail, but this is how it is made. Grinding wheel has self-sharpening characteristics. We say grinding wheel has self-sharpening characteristic. So, you see that this is the thing you have to note, it has got self-sharpening characteristics because during machining active grains get fractured or break away from the wheel and then new grains become exposed and active. So, new grains become exposed and active and this process goes on. Performance of grinding wheel depends upon mainly 4 factors. One is the type of abrasive grains. What type of abrasive grains you are using? There are different type of abrasives, like it can be aluminum oxide, it can be silicon carbide. So, you have to decide which type of abrasive grain has to be used. Every abrasive grain will have different characteristic. Then what is the size of abrasive grains? You have to decide about the size of abrasive grains and we decide types and quantity of bonding material. So, types and quantity of what type of bonding material is there and what is the quantity, means what is the quantity means there may be more bonding material, less number of abrasives or vice versa, and then spacing between the grains like this one. So, there is a spacing here, this is this one. If more spacing is there, means open structure or it is dense structure. Spacing usually need not be uniform also. Here you see that somewhat variation is there, here spacing is less, but you know this will be in an average sense we talk about the spacing between the grains. So, these 4 factors will decide that what type of motion will take place. So, let us discuss one by one about abrasive. Abrasives, widely used abrasives in grinding wheels are aluminum oxide, that we say Al2O3, and silicon carbide, that is SiC. Aluminum oxide grains are suitable for grinding of steels, ferrous alloys and other high strength materials. Aluminum oxide grains are suitable. Suppose you want to grind the steel, you can use aluminum oxide, ferrous alloys are there, and some high strength materials can be machined or ground by aluminum oxide. Silicon carbide grains are used for grinding of hard and brittle materials such as cast irons, ceramics, glass as well as other low strength materials such as aluminum, brass and copper. So, silicon carbide grains are used for grinding of hard and brittle materials, example cast iron, ceramic, glass, and it can also be used for machining of aluminum, brass and copper. Now, about grain size, the size of an abrasive grain is expressed in terms of a sieve number. We basically see that we make various type of sieves. So, from which sieve this grain can pass. Okay. So, sieve may be like this. Okay. That may be, suppose I make a rectangular sieve, it may be like this, and this is a typical maybe size of the opening, and so if this size is more, then that means the number of openings are less. Okay, number of openings are less. So, if we talk in terms of inch, you know 1 inch is equal to 25.4 mm, 1 inch is equal to 25.4 mm. Old system was actually inch etc. In our country also we are using inch, and now of course we have switched over to SI system of unit, but you can know the conversion. So, 1 inch is equal to 25.4 mm. So, earlier suppose sieve number is there, they used to define that how many openings are in 1 inch. Suppose this thing is, let us say if this is 1 inch, then in 1 inch how many openings are there? 1, 2, 3, 4, 5, 6. So, we can give that something like sieve number is 6. Okay. So, you can very well see that sieve number is inversely proportional to the size of the opening. If the sieve number is more, that means your size is less. Then what is the size of relation between mean diameter of an abrasive grain and sieve number is given like that. If suppose mean diameter is G, so G is defined as 0.6 divided by SN in inch, that this diameter will be in inch. That means more the sieve number, lesser the diameter. Example is that a number 30 grain size has a nominal diameter of 500 micrometer, and while the 46 grain size has about 325 microns. Okay. So, this type of relation is there. Anyway, you have to just suppose you can remember this formula, G is equal to 0.6 divided by SN per inch. So, we talk in terms of basically the grains. So, grain size will be that suppose there is a grain size, it can pass through this particular sieve. So, that will be the size of the grain. Okay. Suppose 30 grain size, 30 grain size means it can pass through the sieve of number 30. Okay. It will not pass through the sieve number of 32. Lesser sieves it will pass, because 30 grain size has a big opening and 29 has even bigger opening, 28 has got even bigger opening, but 32 has got a smaller opening. It is just reverse. So, you just have to remember these concepts. Okay. So, we have talked about this one. Now, coming to the bond material and structures. Bond materials provide the required strength and hardness to the grinding wheels, because abrasives are basically loose particles. So, they have to be bonded together. So, these abrasives are bond together, and the bonding should be strong enough to withstand the stresses at the grinding temperature, because temperature also increases, there is a lot of heat generation. So, bonding should be strong, otherwise the abrasives will fragment and nothing will be done, you cannot do machining, but it should provide adequate support to the abrasive grains during cutting, and should also be resistant to chemical attack by the coolant, because we keep lot of coolant, sometimes we give lot of flow of the coolant, that is flood coolant type of thing. So, it should be your bonding material should be resistant to chemical attack, it should not be spoiled by the chemicals. Common bonds are vitrified, which is prepared in a special way by heating etc., and then resonide, rubber, shellac and silicate bonds. And volumetric composition of a grinding wheel can be expressed as VA is the volume percentage of abrasive grain. Abrasive grains have volume percentage VA, VB is the bond material percentage, and VP is the poles or wires, they together constitute 100%. So, VA plus VB plus VP is equal to 100%, and VU. In a typical vitrified wheel, suppose VA can be 50%, 50% are abrasive, VB is 10% and VP is equal to 40%. So, most of the material there is a pole, that means vacuum type thing, means rather wire type of thing. So, these wires they control this one. If VP is more, that means it is having open type of structure, and if VP is less, then it is this one. If we talk not in terms of percentage, we can talk in terms of the fraction also, and in that case this value can be written as 1. So, we can naturally represent by a triangle here, that in a triangle this may be VA point, this may be A, and this may be VB point, this may be VP point. That means, if something is here, that means VA is 100% or 1, and if it is here, the VB is 100% bond, that means it is full of bond material 1, and here that it is full of pole 1. We do not of course always operate in the vertices. Instead, we may have some type of situation like this. Suppose some value, some point is in the centroid, that means here that VA is 33%, VB is 33%, VP is also 33%. So, anyway, this triangle just helps to better understand the things, and depending on that you can design your system. And so, these three constituents means VA, VB and VP. VP is not any constituent, but it is basically absence of anything, that means these are wires only, that means nothing is there, but by wiring there, so it can also be considered one constituents. So, this is these three constituents can be altered to control the structure and grade. Grade means hardness of a grinding wheel. Hardness does not mean in that sense that which you studied in the single point turning etc., or in milling, where you are concerned with the hardness of the tool. Here abrasive is anyway very hard. So, here a wheel will be called hard if it is able to hold the abrasive particle very tightly. That means, even if you apply large amount of force, it is not breaking, then it is hard, and if it can be easily dislodged from the bond material, then that one is soft. That is the meaning of the hard wheel and soft wheel. So, abrasive particle may be same, but one grinding wheel may be hard because bond material is holding it very properly, and another may be soft because bond material is not holding it very properly. So, this is what it goes. Now, we discuss about now the grade of this one. So, strength of bonding is normally termed as the grade of the wheel. If the strength is more, then naturally that it is said that there is high grade wheel. So property is characterized by the mean force required to dislodge a grain from the surface of a wheel. If we want to quantify the grade, we can quantify it by the amount of the force required to dislodge. That if you require more force to dislodge a grain from the surface, then naturally that it is called, its grade is high. Now, grade of a wheel is designated by a letter of alphabet, like A can be soft and Z is very hard. So, we can designate by this one. So, 26 divisions. So, roughly we can do that. Now, let us discuss about, this is very important, grinding wheel specification. We use alphanumeric system, that means we use letters and numbers to characterize a grinding wheel. This marking system for grinding wheels was recommended by ISO. So, ISO has recommended this type of thing. So, let us see what really happens, that first, suppose coming to the first letter A, wheel characteristic, it indicates special grain characteristic, it is optional. Another is grain type A. If I use A, then it is aluminum oxide. If I use C, that means silicon carbide. Like that, there may be different type of letters for different type of abrasive materials. And then coming about grain size. So, grain size also we designate by numbers, grain size. Suppose grain size is 10 to 24, then that is coarse grain. Why 10 to 24? 10 to 24 grain size, that means this is a small number, 10 to 24. So, grain is bigger, as I told a few minutes earlier, that it is reverse type of system. If the grain size is small, that means grain is of bigger diameter, and if grain size is big, that means grain diameter is small. So, 10 to 24 is coarse, 30 to 60 is medium, 80 to 180 is fine, 220 to 600 is very fine. So, this type of system is there. So, suppose I have used 46. So, naturally this particular wheel is of medium grain size, Then we talk about the grade. Grade is suppose this is J, I have used here J letter, but it can be A to G, that means it is soft. If A is there, then soft. B is soft, but less soft than A, like that A, B up to G. Then H to P is medium, and then Q to Z is hard. So, here I hold it in J, A, B, C, D, E, F, G, H, I, J. So, that means it is of the medium size, okay, medium grade. That means strength is medium, okay. That means abrasive particle is not very tightly attached with the bond, but it is also not very loosely attached. It is, you will require some medium amount of force to dislodge the grain. Then wheel structure. Wheel structure means that here you have wheel structure, that means here I have written 5, but it can be between 1 to 4. 1 to 4 means if it is a dense structure, then it may have 1 to 4. Okay. So, that means this is dense structure, then 1 to 4 wheel structure, and then if it is 5 to 8, then it is normal, and 9 to 6 means open. That means spacing between the abrasive grains is very high, then you will be giving something like 16 or something, yes, or 15. That means it is gap is like that. So, bond type is V means vitrified, and B may be resinide, E is shellac bond, R means rubber bond, S means silicate bond, and V means vitrified. And then there may be some manufacturer's reference number, say suppose I have given 10. So, this is some wheel identification, it is optional, it may be manufacturer to manufacturer. Like one example is there, that suppose I say my wheel is AA46J5V8, suppose I have said V8. So, AA means it is a special type of aluminum oxide, and it is white aluminum oxide of medium grain size 46. 46 means grain size is medium, and medium grade is J is medium, and normal structure, that means it is medium structure type of thing. Okay, it means abrasive particles are not very close to each other, but they are not very far away also from each other. They are at some reasonable distances, like this type of thing. So, here this one, and they are bonded together with vitrified bond, and it is this field is suitable for precision grinding. So, we just manufacturer has indicated some 8 designation. So, this type of nomenclature system is employed, and this is how that we go about that. Now, let us discuss about the mechanics of grinding process. You have to little bit visualize and put some effort. It uses a lot of geometry and some trigonometry. That suppose consider a surface grinding type of operation, in which suppose work piece is moving like this and there is a field. Relative motion is only important. Suppose the table is reciprocating or moving in this direction, field may be stationary, or alternatively the field can move, and this can be this one. So, means table can be stationary, but most of the places we use a surface grinder in which there is a hydraulically operated table that keeps reciprocating. That type of phenomena happens. So, this we are calling as feed motion. It is expressed in V, that means it is meter per minute, and the wheel diameter is D. So, this diameter is D and wheel radius is D by 2, and it is rotating with velocity V. And now what happens, that here this one is the depth is D. D is the depth of grinding wheel, the depth of cut type of thing you can call that, where we are giving the field depth basically, and it is a type of that it is called in feed here. D is basically in feed, that means I am feeding that. That means from the surface we are removing D amount of material, D is getting removed. Now, what happens, that suppose it is you have given the depth of this one, and this point is O, and it is digging like this. Naturally, that this point is O is the point of contact here, that means from the surface it is okay, it is on this one, V is the peripheral speed, and then you have got some A, this point is A. Naturally, that this A means that here when it is digging, and suppose up to this it has been machined, so it is contacting like OA. So, but what will happen, that by the time this field goes, this point goes from O to A, that means this is moving, it is rubbing, it is going removing the material O to A. If it was not moving at all, that V was 0, in that case I would have removed, abraded this much amount of material, that is OA. But what happened, that simultaneously this point has moved also. So, that means this B point of the surface has come here, or in other words I can say that if I assume that workpiece is stationary, then my center has moved a bit, and whatever that A point was here, in the meantime it has gone at this point B. So, and in the same time O point has gone to A. So, basically we have not abraded material OA, but we have abraded material OB, basically OB, this much material we have abraded. So, that means this much junk has gone. So, if it moved, there was already some material. So, this material also has been removed like that. So, that means this has been pushed in that way. So, that is why that this is the basically we consider that OB is the length of the chip. That means this is a chip. So, the chip length is basically this, and thickness is naturally perpendicular, that means it is here something like this, here like this. So, thickness is this. If you drop from A perpendicular, that will be one type of thickness. So, you see thickness is varying also, here it is 0, here it is more, like that. But what happens that the length of the chip is basically this OB. So, undeformed chip length L for the various cases can be estimated as L is equal to OB, which is approximately we can say it is OA plus AB, because if this angle is very small, it is a very small triangle. OAB is a triangle, and this triangle is very small in the sense that of very small area, that here OA and OB. So, naturally OA plus OAB will be always more than OB, but as you see, if this angle is much more, like in this case, it is, if it is almost 180 degree, then it is OA plus OB, AB is exactly OB, but it may not be 180 degree. These two angles are very small and this angle is very big. So, approximately L is equal to OB, that is OA plus AB. Now, we have to estimate. So, if we want to get the length, we have to estimate what is OA and what is OB. So, assume that time tau is the time taken for the wheel to travel the distance OA. That means point O reaches point A in time tau. So, OA is equal to naturally V tau. V is the surface speed of the wheel, and in meantime this point AB, this movement will be there. A point has gone actually to B because the table is moving. So, that AB is equal to small v times tau. So, V is the work speed and capital V is the wheel speed. Capital V is much more than small v. Now, eliminating tau from both the equation, we get a relation AB is equal to small v by capital V multiplied by OA. So, we can put it there, and if we put in this expression, then we are getting L is equal to 1 plus small v by capital V OA. So, approximations are of arc OA. Now, suppose so we have to only find out OA. Now, how do we find out OA? Well, finding OA is very easy because we can use the Pythagoras theorem. So, OA means this much and OA is equal to, so suppose I say I drop this one, this triangle. So, OA is equal to D square, that means perpendicular square, into this base thing. So, base thing means that this one, suppose OM, so that means AM, that one. So, that means this half the chord length AM. Okay. So, this, so OM, that means D square, that is okay. Now, AM is square we have to write. So, AM is how to find out? By Pythagoras theorem. If I take a center and join like this, so here if it is suppose it is O dash center, O dash A, that means D by 2 square minus O dash M square. O dash M is what? From here to here D by 2. So, D by 2 minus D. D is the wheel depth. So, D by 2 minus D whole square. So, this becomes D by 2 square minus D by 2 minus D square plus D square. Like that we can do, and after that we can simplify this expression. So, we can say that yes, D by 2 square. So, this becomes D square by 4 and minus D square by 4 minus D square plus DD. So, we get OA is equal to DD. So, OA square we get DD because this cancels, D square is added here, that D square was here. So, this D square got cancelled here, D4 got cancelled here, and you are left with DD. So, that is why we get OA is equal to under root DD. Of course, I must call OA not equal to under root DD, but OA is approximately under root to DD. Why approximately? Where is the approximation? We consider that OA like a straight line, whereas there is some curvature. Of course, the wheel is of big size, so OA will be more or less, it will look like a straight line only, because even if I make in this figure, OA comes like this. So, it is very OA arc and OA line is basically same, almost same. So, for horizontal surface grinding, this expression is okay and D is the in feet. Now, the chip length LS for this case becomes, if we put that and we say chip length, now I am using the LS, so subscript I am using S. So, why I am using that means it is surface grinding. So, surface grinding means LS and that is 1 plus V by V already I wrote under root dB, D under root dd. So, that means the length of the chip will be increased if the field depth increases or the diameter of the field increases. And well, it is also, if the feed is more, that means V is more, naturally the length of the chip will be more. And if you know that feed is if that field speed is more, then it is having slightly less effect. Okay. So, that means suppose V is much more than V is much more than V, then chip length simply becomes LS is equal to under root dd. So, that is how that it goes. So, for external cylindrical grinding, the cardinal length OA can be evaluated using triangles OA A prime, OA A prime and O double prime A prime, A prime. So, that means similarly we can extend that theory to cylindrical grinding. Suppose we have got this as a job diameter. So, dW is the diameter of the workpiece and the distance is dW by 2, this radius basically of the job. So, work that is job, and this is rotating by a very dW is the work diameter, remember that, and it is rotating with a surface speed of small v, like in a surface grinding, small v, same symbol we use, and wheel speed as usual is capital V, and this is center here, this is like that. So, in that case, when I am rotating, then I am concerned about finding out that basically that this one is OA, means that this distance. So, this will be so this will be OA on this one. So, we want to get about OA. So, OA is OA can be evaluated like this. OA is equal to, in this case, d by 2 square minus d by 2 minus OA prime. So, d by 2 square OA. So, that means d by 2 here, and this is d by 2 minus OA prime square. So, that means whole square. So, this will be basically what will be that OA square, that means O prime A square d by 2 square, and you did minus d by 2, this one minus this much. So, you got this horizontal distance, but then if you do that OA, then you also did OA prime square. If you do OA, this is OA, this is OA square. OA square is this much only, and if you do OA prime square, that means this and this square, then you get AA prime square. So, basically you get AA prime square. So, this should be AA prime square, AA prime square. This I am correcting online here. So, AA prime square, and if you simplify this, you cut that it will be basically d time OA prime square. Also, OA square is like this. Suppose now from this one, if we get dW by 2 square in the same way, and then we say dW by 2 square, suppose from here to here, this one, and minus dw by 2 minus small d and plus plus OA prime. So, plus OA prime we have added, and plus again so this much if we do, then we get this one OA prime minus and then minus d square. So, we get minus d plus OA prime and plus OA prime square. OA prime square I have added. So, again you will be getting from here another expression, and that will be AA prime square, and this will be dw by 2 minus 2w OA prime, where d is the wheel diameter and this one from this one. So, substituting from this to this, we have got okay. So, this is yes. So, this if we substitute both the thing, so we get and we simplify. So, we get that basically AA prime is equal to this one under root d by 2 under root d 1 plus d by dw is this one. Now, what happens that here this is basically this will be like this one, and this will be like in the previous case. This will be chip length for external cylindrical grinding is obtained by putting this expression, that 1 plus in the similar way V by V, and this is OA and this one is like that. So, we get only this type of expression here, that you have to see little bit carefully, that in this I think it was OA square and OA square, they are writing O was the basically the contact point here, that like this OA, O, and then O was this one OA. So, this was like this OA square. So, this was yes, here this is was the it is making that contact AA square. Okay. So, that means actually it was corresponding to something like that, like here O goes from A. So, similarly here that contact point A dash is going to A here, and that is what that this is the thing. I think there was some misprint in the that your textbook also, but this you have to understand very correctly that this is A dash, and then finally it is going to that here A, and the length of the chip will be basically A dash A and AB and A dash B. So, it is like that in that fashion. So, that is what. So, it should be actually AA dash, and then it will be consistent, and then you will be having, suppose I put AA dash, and AA dash expression is this one, and 1 plus V by V is this one. So, hence the chip length for external cylindrical grinding is obtained as 1 plus V by V and under root this one. So, we got this expression. This expression has to be reduced to this one surface grinding if dw becomes infinite, because there is infinite. So, dw is equal to infinite. If we put, we get back the same expression. Similarly, if we do this type of exercise, then for internal grinding we can obtain a similar expression, and we can say Li is equal to 1 plus V by V under root dd 1 minus d by dw. So, if work speed V is much smaller than wheel speed V, then the chip length can be written as Ls becomes under root dd. Okay, because this portion will be almost this one. Le becomes this thing dd 1 plus d by w, and Li becomes dd 1 minus d by w. So, Ls is the chip length for horizontal surface grinding and Le is the chip length for external cylindrical grinding, and then Li is the chip length for internal cylindrical grinding, d is the field diameter and dw is the work diameter. Now, let us find out some expression for the chip thickness. Chip thickness significantly influences the grinding energy, field wear and surface finish, etc. We assume that all chips are of the same average size, that means width wise it is same, B, suppose wheel is there, so width wise it is same, and chips have constant width B. Now, volume of an individual chip, suppose we are cutting, you see that chip thickness is gradually increasing. You can see that here it is cutting like an arc, na, here from here to here. So, somewhere and it is moving also. So, that means here it is not cutting much material, but when it has moved, so this point has gone here. So, here the thickness is much more. So, we are assuming that it is gradually increasing and let us say the maximum thickness is T. Okay. So, in that case, this will be T is the undeformed chip thickness, and in that case what will happen, that T by 2 is the average type of thing, and volume of this chip is equal to Ls, if the L is the chip length. So, we will say Ls half Ls into T by B. Okay. So, it will be that basically average this one and width is B, and we can say that it can be, if we define R is equal to B by 2 T by 2, we have defined like this, then it can be called as Ls T square R by 4, where T is the undeformed chip thickness, maximum thickness. And chip volume can also be calculated as volume of the chip is equal to rate of metal removal divided by number of cuts made per unit time. So, metal, suppose the wheel width is B and V is the surface speed of this one and D is the depth. So, V into D into B, that will be the volume of metal removed, and if we make mean time, if suppose there are C number of active grains per unit area, if there are C number of active grains, then number of cuts made in unit time will be V into C into B, because C is in per unit area. So, you know that in per unit time, suppose this covers a distance V, so VB area it covers, so VCB divided by VC. So, that means that volume of chip then we can obtain, okay, because each abrasive grain is removing one chip, and then we are getting like this. So, VD divided by this one, and then we are giving this one. C is the number of active grains and B is the width of the grinding wheel in contact with the workpiece. So, chips produced in horizontal surface grinding has been shown here. Schematic view of the process is this. Idealized chip is actually this. So, chip length I am assuming like this, but here chip width I am assuming B. There may be many active grains parallel wise. So, that I am assuming this one, and actual chip is actually of this shape. So, that means the its width is we are assuming that actual chip, suppose here it is width is B, and we are assuming that chip width is B, and this actually should have been thickness actually. So, this is in fact T by 2, okay, that means this is T by 2 will be the thickness, but actually this is okay, that means ideal actual chip, okay. So, I am showing that we are idealizing like this B, but we are having actually the chip like this, that even the width is also may be changing, okay, that may be situation. Now, what happens from equations 4 and 5, if we volume of chip we have got, and this is also we got, equate these two. So, we get T square is equal to 4V divided by VCR and divided by dLs, and if we substitute Ls is equal to under root d by d. So, we get basically T is equal to this thing. So, we get that chip thickness is actually will increase if small v increases, but if capital V increases it will reduce, and if the more number of grains are there in per unit area like C is more, then also it will reduce. R is equal to, we have assumed a parameter that is the aspect ratio type of thing, it is B divided by T by 2. So, if R is more, naturally the chip thickness will be less, and it is also dependent on D, and capital D is the wheel diameter. If the wheel diameter increases, the chip thickness will reduce, and square root type of relation is here. The value of T for all types of peripheral grinding operations can be obtained in a similar manner, and the expression for T can be written in a general form. So, T is equal to, we can write 4V, and this is how that means it is for cylindrical grinding. So, you want instead of under root d by d, it will come here, and so dW is infinite for surface grinding, positive for external cylindrical grinding, and negative for internal grinding. So, we have now these cutting point C, that how do we obtain C, that which we said that about this one, C is the number of active grains per unit area. So, methods to determine the number of active grains per unit area is like this. Simplest way of determining C, the number of cutting points on the wheel surface, is to roll a dressed wheel. That means, we have done the dressing operation, that means, we have sharpened that wheel by a diamond dresser, and then we take a soot coated plate. Just we put a soot, that what we call in Hindi kajal, and in that we just put here, and then we roll it over, and we count the number of contacts indicated on an enlargement made using the plate as negative. So, we can see that, and we can, after that we see that high spots will take the soot away. So, that means, you will get the idea from that place that soot will go away. So, you can number of so you can actually know that type of thing indicated. So, this is what you can get that. Another method is to count the number of chips produced in a given time, that if you can do. A better method is to count the number of wheel threads produced on the wheel surface. We can see how many wheel threads are there. That means, it will be visible on the grinding wheel surface, that those portions will be flattened many places. It is observed that the grain density, means number of cutting points per unit area, initially increases steeply as the chip thickness is increased. As chip thickness is increased, abrasives are dislodged and more active edges come, and then it tends to remain more or less constant. So, that type of thing is there. Now, we discuss about grinding forces and specific energy. So, forces acting at the wheel work interface can be easily measured with the help of a 2 or 3 component workpiece diameter. Now, figure is showing 3 components FP, FQ and FR using horizontal surface grinding. When the workpiece width B prime is less than the width of grinding wheel B, which is not the case here. Here B prime is much more than B, but in other case there will not be cross feed, no cross feed will be needed, and FR component will become 0. In this, FR component will also be there, and from measured value of grinding force Fp, we can find out energy. Fp into V, V is the surface velocity of the wheel, that gives the energy. Fp into V and divided by VBD. VBD is the volume removed per unit time. So, if you divide U by this one, that power divided by this, you get a specific energy. A specific energy means energy needed to remove the unit volume of material. So, this is the expression you are getting. Now, it has been shown experimentally that specific energy in grinding increases rapidly when chip thickness T is decreased. Like here, it is increasing very rapidly. For high chip thickness, it is less, but then it increases. That we call so-called size effect. When a specific energy values obtained in grinding are plotted against T on a log-log graph, the variation is seen to be linear. This gives a relation in the form UTM is equal to constant or U is proportional to 1 by Tm. So, when a specific energy values for fine grinding, rough grinding and single point cutting are plotted together, a continuous curve as shown in this one is obtained, and this curve indicates the exponent m in the rough grinding is about 0.6, while in the single point cutting it is only around 0.2. So, this shows that size effect in grinding is much more. Now, wheel wear and grinding performance. For fine grinding, the stages of wheel wear W with respect to material removed Wm is shown in figure. So, volume of wheel wear and volume of work material removed is plotted here. G is the grinding ratio, that is volume of material removed divided by volume of the wheel removed, wheel material removed. So, this is what in the beginning G increases rapidly, then that means volume of wheel wear means increases rapidly, because that is break-in period, because lot of wheel wears, and after that there is a constant uniform wear region, and then after that final breakdown occurs, and this is what you are going here. So, this is just like a typical in cutting tool also the same type of curve you get. So, first phase indicates rapid wear of the grinding wheel, and the wheel quickly attains a stable grinding condition when phase 2 is reached. Phase 2 pertains to the linear portion of the curve, where rate of wheel wear remains constant. In the third phase, the grinding wheel becomes dull due to loading and develops a glazed appearance, resulting in the production of reduction of material removal rate, and that means wheel will wear more. So, this phase signified by increase in grinding forces, excessive vibrations and appearance of grinding burns on the ground surface due to high temperature. So, this phase has to be avoided. Okay. Do not grind in this region, this phase is better. Okay. Now, what are the wears of the grinding wheel? That means atresia wear. We told that it is basically due to contact and rubbing. It occurs at the grainworks piece contact surface and is gradual wearing away of the sharpness of the cutting points, resulting in the formation of wear threads on the grain tips. Now, atresia wear is due to micro fracture of cutting points, plastics flow in grain tips, not plastics flow, it is plastic flow, and crumbling of sharp edges get crumbled. Now, we go to fracture wear. When the stresses on the grain increase to a sufficiently high value, the grain fracture fragments and fresh cutting edges are exposed like this. This is called fracture wear. See, this is fracturing here. No? Grains get pulled out of the band when sufficient force is applied at the grain tip. And then there is a band fracture wear. That means this is the band here, dark portion, and these are the grains which are attached. So, pulling out of the grain would be due to fracture of the band post rather than separation of the wheel. So, that means they get removed together. This is this one. So, we show three types of wear: atresia wear, grain fracture. Atresia wear is shown here in the A portion. That means it is just gradually wearing and producing some wear thread. Grain fracture means grain gets broken in between, and band fracture means band gets broken. Now, about coming about force calculation on a typical grain. Assuming that the tangential force Fg on an individual grain to be proportional to the area of cut AC, that is, suppose Fg is proportional to AC. An area of cut can be taken proportional to width of this one and thickness T, Bt, and since B is roughly proportional to T, that means if width is more, then naturally we can assume that maybe thickness is also more, or if thickness is more, then the width is more. So that means it is proportional to T square. And if we put the value from equation 7, what was equation 7? That means here it is that type of here equation 7, that means expression for T is there. So use the expression for T, then you get basically this type of thing. Fg is equal to kg V divided by this thing, and kg is a constant, B is the average chip width, and T is the undeformed chip thickness, R is a type of aspect ratio. So for surface grinding, we get Fg as Fg is equal to kg V divided by this much, and we get this type of. So we see that force will be much more if the depth is more, but if the wheel diameter is more, it will be reduced, and it is proportional to small v, but inversely proportional to capital V. If more number of grains are there, then the force will be reduced like that. So if the wheel wear is excessive, suppose wheel is wearing the excessive, so what you should do in the shaft floor? You should ask the operator to reduce the table feed, that means V. Table should reciprocate slowly, and D should be decreased. But if suppose wheel is getting grazed, that means it becomes graze type of thing, means it loses its sharpness. It will look shiny type of surface, and you will see that yes, this is that there is a grazing, it just rubs. So that means V and D should be increased, so that more force should be produced and the grain should be dislodged. So a typical experiments results showing the variation of wheel wear with number of passes during grinding process is shown here. Here volume of this one. In these figures, phase 1 and phase 2 are clearly shown. Obviously, the phase 3 has not been reached. I told that we should not do the grinding operation in phase 3. These figures further indicate that the wheel is cutting efficiently during phase 2, where wheel wear increases linearly and forces remains more or less constant. So force is shown in the beginning, the force increases, then more or less it remains constant. This is cutting force Fb and thrust force is Fq, and this is shown with this one. Now variation in grinding ratio G with wheel grade for 3 different work material is shown here. In all cases, G increases initially as wheel hardness is increased, that means grinding ratio will be high, that is good, but decreases with further increase in wheel hardness, because then it will cause grazing type of thing. So there is optimum value. As the wheel hardness is increased, wheel first grinds in the self sharpening region, where later in zone of mixed conditions, partly sharpening and partly blunting. We need sharpening operation, not blunting operation. In the final range, blunting dominates, resulting in increased wheel loading and reduction in material removal rate. So this is what it has been shown, and you see that it is 17 RB, that means and this is 29 RC, this was 29 RC, and this is what this one. So it is depending on that material, your characteristic will also differ, and this is wheel hardness increases from G to N. Okay. So it is like this here. The variation in grinding ratio G with grain size also is shown, increases initially with grain size, but reaches maximum, and then with further increase in grain size it reduces. It is similar to previous curve. For a given material, there is an optimum grade and there is optimum grain size also. So this has been shown here. Now grinding temperature. When the grain first contacts the workpiece surface, sliding and ploughing of the surface layer occurs, and then as the chip thickness increases, the force increase and a layer of material is removed in the form of a chip. grinding temperature rises due to following reason. Heat is generated in the interference zone due to plastic deformation and frictional sliding. Then heat is generated as the chip formed traverse up the front face of the grain, and due to these very high temperatures are recorded near the cutting edges. You can see these small chips will fly like fire sparks. As a consequence of high temperature, not only the field wear increases, but large residual tensile stresses may develop. So, this is large tensile stresses are not good. Now, we discuss about surface roughness. Surface produced on horizontal surface grinding machine consists of scallops left on the workpiece due to finite spacing of successive grains. If all grains are assumed to be at the same radial distance equally spaced, the plan view of finished surface will consist of an array of cylinder shaped scratch as shown in B. So, you will get this one, this type of situation you will get, and we are getting this type of shape, and this is SF by 2 that feed here. These are scallops on the ground surface, and plan view of scratches are shown here. So, here assuming the midpoint of the scratch to be the deepest point, the idealized mean peak to valley height h can be evaluated. If there are C number of cutting points per unit area on the field surface and average chip width is B, then the distance between two cutting points on the field surface will be 1 by BC, and the distance between two cutting points on the workpiece will be small v divided by VCB. Then distance SF moved by the workpiece between passages of successive grains is SF is equal to V divided by VCB, and this is 2V divided by VCRT. That means we have got SF this one, and then distance SF in terms of H can be evaluated from triangle ABC like here, and this is SF by 2 d by 2 square d by, so SF is equal to under root 2 dH. So, equate both the portions, H is this, so you get H is equal to this much, and substituting the expression for T, we get H is equal to T square by 16D. So, that means basically this that peak to valley height H, that is proportional to T square, but it is 16 by D, that means inversely. So, that means if you take more depth of cut in fact, then your surface finish will be good. Surprisingly, this comes like this. Why this will be good in that sense? Because more cutting force and this will activate and this will large. Of course, T itself is also dependent on under root D this one. So, T is in fact basically T square is proportional to under root D. So, if I put that thing also here, then it will show something like this, H is proportional to 1 divided by under root D. So, that means anyway that if you take more depth of cut, it will be better, it will produce more this one force, it will produce more force, and it will help in the dislodging, and it will activate the self sharpening action. That is what that this simple mechanics analysis shows. And another thing is that this thing you also remember that the hard wheel is employed for grinding of the soft material, and soft wheel is employed for the grinding of the hard material. Why? If the material is hard, it will cause flattening of the abrasive particles soon. So, we want those, let them dislodge fast. So, better make a soft wheel, so that it will dislodge and new edges will come. Whereas, if the material is soft, then lot of chips will be generated, and we can afford to get hard wheel, so that unnecessarily the wheel does not dislodge, and they can do. Similarly, about the structure also, if it is a soft and ductile material, we can have a bit open structure, otherwise we can have dense structure, like that. These type of concepts are there. So, we have discussed about the grinding process, and we will continue our discussion in the next class.